Hello and welcome to Function Families, Putting It All Together. This is where we're going to recap all of our understanding from the different patterns between our function families. So we first need to know some of the names of the families. The first family that we looked at was linear, then quadratic, exponential, inverse, and then there's that last absolute value family. It's kind of the imposter family. We're going to touch on them at the very end. So we're going to be identifying our functions based on the equations, their graphs, and the tables that they create. So first, let's look at some of the equations. Some examples of linear equations are the things that we're used to. Y equals x, y equals 2x, y equals 7. These are the standard y equals mx plus b equations, where all we're doing is we're taking our x and we're just multiplying it by a constant number. Or in some cases, we're going to have y just be equal to a number. So in quadratics, our equations are going to be things like y equals x squared, y equals 3x squared, plus 4x minus 7, or we can get creative with some parentheses, like y equals negative 4 times x minus 3 squared minus 6. Notice that in all of these, we are taking our x value and we're squaring it. We have that squared value going on between each of the different functions. Though in this last case, we don't directly have the x being squared. Because it's in those parentheses, it will come out to be an x squared if we multiply that out. For our exponential equations, we have things like 2 to the x, 3 to the x plus 4, or 2 to the x power plus 1. In all of these, notice how we have x up here in the exponent. So the way we can tell the difference between exponential equations and anything else is if there's an x in the exponent, then it's going to be exponential. Notice that exponentials are not like quadratics in the fact that quadratics, x is the base, and we have that squared value up in the exponent, whereas in these we have x going on in the exponent. So inverse equations turn out to look like our fractions. 1 over x, y equals 2 over x plus 4, or y equals negative 5 divided by 2x. In these, look where the x is. It's in the bottom half of our fraction. It's in the denominator. And that denominator is going to do some interesting things when we get to the tables and graphs. So speaking of graphs, let's go to some linears. So linear lines, this is where we have linear or line equations. We have a positive slope, we have a negative slope, or we have something that's no slope. Remember how I said y equals 7? In this case, it's y equals 4. If you look kind of closely, you can see it going through that 4. For quadratics, we get these kind of horseshoe-shaped things. These are called parabolas, and they can be going positive, they're making smiles, or they're negative, they're making frowns. But these are called parabolas. These, if you have a parabola going on, it's going to be a quadratic equation. Exponentials kind of have a similar curve to a quadratic, but it just looks like 1/2 of a curve. The curve is slightly different from a quadratic curve, but that's getting into a whole lot of detail. For these, we're going to have one line and it's going to curve up. Notice over here on these graphs, these are two different graphs, by the way, the blue one and the red one. And notice how the blue and the red lines are getting closer and closer to a certain number. That's one of our vocab words. That's called an asymptote. Later on, I'm going to make another video going over a recap of all of our vocab terms. So, graphing our inverse, these were the weird ones that we kind of got excited about in class. So this is where we're getting two different lines going on. Usually they center around the origin. Remember, origin's this thing right here in the middle. Again, that's going to get into some of our vocab terms in another video. But we have two lines going on that are in, interesting header. We have two lines going on. They're in opposite quadrants. They are curving away from this thing in the middle. We're going to get there when we look at our table. And they're kind of shying away. In this, we actually have two asymptotes. We have a vertical asymptote right here, and we have a horizontal asymptote right there. So if you've watched this far into the video, part of the homework is to take a survey. Part of the survey is to just answer this question. It's going to be your name, your advisor, or your name, your block, a fist of 5 about this video, and answering this survey question. So for linear, we can look at our tables. Our tables, if we look at a linear table, this is just the standard y equals 2x plus 5. We can tell that it's linear by looking at this thing called a first difference. Sorry about my pen on this. I don't have a good pen at the moment. We have the difference between 1 and 3 is 2. The difference between 3 and 5 is 2. 5 and 7, 2. And 7 and 9, 2. We're adding 2 to every step to go down our graph. So hopefully, if you were doing this by hand, you do the first couple, you notice the pattern, and then you just keep adding 2 as you were going down the equation. So, quick recap of linear. We have a constant first difference. This first difference ends up being our slope. So remember y equals mx plus b. That plus 2 becomes that m. And our y-intercept, that's going to be right here. So the 5 goes right there. That's our b value in mx plus b. Hopefully this is just a review for those of you that were in Division 1 MST. For quadratics, if we're looking at the table, see how we get a couple of different patterns going on. Notice that we have this mirroring effect, where we have 4, 1, 0, 1, 4. It's mirroring around a certain number. That's pretty classic quadratic right there. But if we look at our first difference between 4 and 1, negative 3. Between 1 and 0, negative 1. 0 and 1, positive 1. Notice that before, as we're getting smaller, it's negative. Now when we're getting bigger, it's positive. And, I'm sorry. Instead of plus 4, it's actually plus 3. So our first difference is not constant. So we have to go down and look at the second difference. We have negative 3 to negative 1. Well, this is where we're adding 2. Between negative 1 and positive 1, we're adding 2. And 1 and 3, not 4, is positive 2. So in quadratics, if you have a constant second difference, that is classic quadratic, as well as that mirroring effect around this part right here in the middle. When we get into our quadratics unit, we're going to look more at why that happens and what's going on. And finding the second difference is just like finding the first difference, but after you do it the first time, you do it a second time. So exponential equations, this is where if we look at the first difference, we're not going to have a constant thing. If we look at the first and second and third and fourth, it's always going to be not a pattern. It's not going to go to a constant number. Instead, we have difference between 1 and 2, multiplying by 2. Go to 2 to 4, multiply by 2. You could even go down here in this fractions, go from quarter to half, multiply by 2, half to a whole, multiply by 2. I'm getting a little bit too tight for this pen. But exponentials, if you're progressing and you're going down by a constant multiple as opposed to a constant first or second difference, it's going to be an exponential equation. Oftentimes, our exponentials will stay positive unless we start having a negative thing appear in front of the whole equation. Wrapping up really quickly, we have some inverse tables. In our inverse tables, They look pretty big. It's actually a whole lot easier to look at inverse tables with fractions as opposed to the decimal number, but as we're looking at it, we'll just look at both of them. Notice in our inverse, we get this error. So if you start getting errors in your table, you probably have an inverse equation. Because really, what's happening to cause this error is we're trying to put 0 into our equation. And are you allowed to divide 1 by 0? You have one thing, and you need to give it to 0 people. How many things does every person get? You can't do it. You can't split one thing into 0 piles. So if we try and divide by 0, we're going to get an error, our calculator is going to revolt, and it's no good for everybody. Oftentimes, x is going to be 0 at the error. Other times, as we shift a graph around, it might not be centered around 0. Remember how when we were looking at the graphs, we had this thing where we were going through and we'd shifted the center bit. Sorry, I thought I had paused during all that, but apparently I didn't. If we have this center thing and it's shifted, that means that we're not going to be having that error at 0. In this case, the error is going to be happening at 2. So this is probably, this graph right here is probably something like 1 over x plus 2. Sorry, 1 over x minus 2. So if we go back to where we were, we can also know that over here, this is going in opposite directions. Right here, this, as it's progressing down, is going to get smaller very quickly. And over here, it's going to be getting larger, but it's getting larger at a smaller rate. And the final function, one that we're kind of interested in, but we're not really going to be looking at a whole lot, is the imposter family. This is called the absolute value. It's a function that can be applied to any other function. So the absolute value is something that we do to other things. We put these straight brackets around an equation, and it says that we're taking the absolute value of it, meaning that we're going to take everything on the inside and make it positive. If it's already positive, we leave it alone. We don't want to mess with things that are already happy. So absolute value takes something that's negative, makes it happy. In our table, it's going to have a similar pattern to the host family, but we're going to notice that in the y, it's always going to be a positive value. And we can get some really interesting graphs with it. So, for example, here's a graph of a linear line, but instead we've made it positive. So if this was in the linear family, this would be continuing that way. Notice how we just took this half down here, and we flipped it around this axis. We just made it positive. Here's a quadratic that if we were to sketch in the quadratic, it would be like that. But instead, we've taken the absolute value, we've folded it over that x-axis, and we've made it positive. Or we get kind of funky, and this is an exponential curve that would be going down like this, and then going asymptotic, but instead, we're making it positive. So thank you for watching the video. Please don't forget to take the survey and get credit for watching it and complete your homework. All right, thank you, everybody.